Since the recording has just started, so I'll speak up something for recording. So we are starting the second day of SPARC series, hands-on modeling of polydispersed multiphase flows, and today we have a hands-on session with Fluidity FEM code. So for that, we have created a virtual machine, and we'll be using VirtualBox to open the virtual machine. So now that we have this, we can add. So go to the add button, click it, and then Sandeep, where have we put desktop? So for us here in the lab on the desktop, we have the virtual machine. So there's a folder called Lubuntu. In that, we should have a large file somewhere. Oh, this is Sandeep. This one. Let me check. Okay, so it has it. Okay. So I should import in that case. Yeah. So I think if we add this, it should add the virtual image. So once you add the this VirtualBox machine file, machine definition file, it should automatically take in the whole configuration. That configuration will include hopefully this large virtual image, which is around 2.5 gigabytes in size. So let's see if you can click start and something happens. So I have got an error. So I think what I did was I created the virtual image on some other machine, and it's trying to access some settings which may not be valid here. You can see invalid settings, the USB problem. Let's go to the settings here. Usually it's very nice. It tells us what the invalid settings are. It says USB 2.0, 3.0 is currently enabled for the virtual machine. However, this requires some extension pack which we don't have. So easiest thing is to disable that. Let's try it again. Right. So if the virtual image is being accessed properly, then you should be able to see the screen where it is asking for a password. It's as if you have switched on a Linux machine. Disable. Sandeep will tell you.
Sir, one doubt.
Yes, please.
So actually, I have downloaded .vbox extension only. During the .vda extension, it was failed. So again, now only I'm downloading.
Okay. You take your time. Okay. If you have any questions, you can again stop me and ask me questions. No
Sure,
problem.
sir. Thank you, sir.
So the password is geek. I'm logging in now. So you can change the settings for monitor if it looks too huge, the icons. You can go to the start menu in your Ubuntu machine, go to LXQT settings, go to monitor settings, and then that should give you different resolutions of monitor. So choose whichever is the best for you. Okay, so I'll go with this resolution. It's too huge, then you'll have to make it enough that fits the screen. Sandeep, is Hemant still here? Yeah, check because I will have a pain in the neck if I keep looking like this. That those two ports that you have above, they're also video ports. So if he has a cable for that, then we can connect this screen as well as the monitor, so I can look at the screen, not the monitor every time. Painful. Right. So I hope everybody is able to now settle down the things with this virtual machine. So you may face issues with the amount of RAM because, as I said, I created this virtual machine on my local PC, okay, in my office. So the RAM settings and the processor settings are as per my machine. If I had set 16 gigs of RAM, and the machine that you're using the virtual machine on only has 4 gigabytes, so then it could be a problem. So go to settings in the beginning and just set everything so that it fits and the virtual machine starts. If it starts, it will work. Okay, so we have set the monitor resolution now. So now, before we actually start doing population balance kind of work, we'll get warmed up with the software first. So in Linux, it's always useful you use command prompt, but we'll use both for comfort. So first, let's go to this folder Geek. So Geek is the name of the user on this virtual machine. And go to GitHub, and there's a folder called Fluidity. In Home, Geek, GitHub, Fluidity should have a folder which has all the files in it. Alternatively, I can launch the terminal. I think it's Alt Control T. And then I can check my present working directory. So I can change my directory to GitHub and then change it to Fluidity. And then do an ls to list all the files I have here. We see the same files. It's the same files being shown on terminal as well as in the folder GUI. So let's work with terminal. So what we want to do now is first we want to look at the manual, okay, a PDF which has all the details about Fluidity. So that will guide us through the steps. So for that we should have a folder somewhere called manual. So cd manual. Let's do an ls. It has lots of files in it. So let's look at only the PDF files. So star.pdf. So I can do a ls star.pdf with minus lar. So that will give me details of all the files in terms of when they were created, what is the size, and so on. So I'm looking at the one which is called fluidity underscore manual.pdf, which has the highest size. If you use H, you will get the file size is 9.7 megabytes. That's the largest file you have here, 9.7 M. We want to open it. I'll also do it in the graphical user interface mode. So go to Fluidity Manual, just click it and open it. Okay, that should open the PDF. So I'll give the users here some time to open this. You can ask me. We are going really slow right now because I want everyone to be able to understand what's happening. So in case you would want to open from terminal, you can write qpdf view. So you type qpdf and then just type a tab. Should complete it, and then write fluidity underscore manual dot pdf. So that opens the manual for us. It's just alternative way to open the manual. Now that we have the manual open, we have different test cases or different examples installed in Fluidity by default. These test cases are used to check if somebody, for example, adds a new feature or changes a feature in Fluidity code. We want to make sure that earlier test cases, earlier features do not stop working because of a new feature. It has a very wide application. So new features should not kill the old features. So for that, we have certain examples or test cases already there. So whenever somebody changes the code and commits it to the main master branch, then those test cases automatically have to run, and you have to make sure all of them pass. And if they all pass, then your new feature is accepted. But for us, we are simply going to use those test cases to understand the software. So if you go to the manual, the reason I'm showing you the manual, not telling you those things, is because later you can refer to the manual again and learn things. So in this manual, we should have table of contents somewhere. Yeah, so it's a very nice table of contents, and it has different chapters. So if you want to get started with installing it, some information is there, how to run it, and so on. It talks about the model equations, different kinds of equations allowed in the software, available in the software. Then discretizations, what sort of discretizations are there. Chapter 4 talks about parameterization. So you'll have turbulence models here, K epsilon and LES models. Then it talks about some embedded models where we have included details of population balance modeling. So everything that I discussed with you yesterday is included here. So if I click population balance modeling, it has the equation. It has what are the different source terms available. So the growth term, which has the derivative with respect to the internal coordinate. Then we have breakage and coalescence terms, as we discussed yesterday. We have the solution method. Okay. Zoom into it a bit. Then we have the complete equation. If you substitute, then we have the transport equations for weights and weighted abscissas. We have the linear system A alpha equal to D. We have how the source terms, etc., are handled here. Then how it is implemented in Fluidity. So the matrix forms, all these numerical details are there. So whatever we discussed yesterday is there in this manual. So I made sure it's available in the manual. That's the good thing about an open source software. So when this software was made available to us, this feature was not there. So we implemented the feature in the software. We added some test cases that we'll run today. We modified the manual, and it's available to everyone now. That's the beautiful thing about open source. We contributed to a software, and everybody now uses it all over the world. I suggest, if you learn the software and if you are going to use these models for some other application and you plan to modify the code in some sense, even minor sense, you can always implement those changes in the code and commit it back. We'll go into the complete software. Okay, so so now that I've told you, let's go back to our table of contents. So we look at examples today to start with. So this was embedded models. Then we have meshes. So if you want to learn about how are meshes being created and so on. So these meshes are created in a software which is outside Fluidity. But all those details, because those software have to be used to create meshes that are then required in Fluidity. So details about Gmesh that again we'll learn today in some sense is also available. Adaptive meshing, we'll touch upon that today as well. Parallelization is all there in this chapter 7. Chapter 8 talks about configuring Fluidity. And then let's go to the next chapter. So chapter 9 talks about visualization and diagnostics. If you want to visualize your results using some some animations or some plots and so on. And finally, we have examples. So we are going to look at a certain number of examples, and you can yourself explore further other examples. The good thing about examples is, see, whenever you want to start working on or start modeling a problem that you are working on, you will not work with a blank scratch file. It's very difficult to understand that. Even if you write a code for yourself, you always start with some standard code and you modify that. So the same thing is what you do here. You pick up an example which is closest to your work, and then you modify it gradually until it reaches that stage that is similar to what you are working on. So that extra change is what is required. Don't start from a scratch zero. Otherwise, you have to understand each and every option, which becomes very difficult task. Right. So let's pick one of these examples. Let's start with a simple one. So we have something called a lock exchange. This is multi-phase. We have a lid-driven cavity, that is single phase. We have a 2D backward facing step, that is single phase. And we have 3D backward facing step. We have flow past a sphere. So for those who have done fluid mechanics will understand these test cases. We have a rotating channel. We have water column collapse. We have ocean convection. We have tephra settling. That's again a multi-phase, very interesting multi-phase exercise example. Then we have some other instabilities and so on. So let's pick up water column collapse. So this one is multi-phase, but let's start with multi-phase because that's what you want to work on. So if you click it, I'll give you some time to go to the water column collapse example and then briefly go through it. And then in a few minutes, we will start working on it. Now, for those who are online, is there any question or issue with this manual?
Sir, this is Ramachandran.
Yeah, yeah.
Yes, sir, I thought to do it in Linux. I have a Linux operating system also as well. But later I am going to do it. So initially I thought to listen and learn everything what you are
Okay,
teaching.
if you have a Linux machine, is that what you're saying?
Yes, sir.
So what you can do is you can download VirtualBox for Linux. That is available.
Yes, sir. Now only I am
You
seeing that.
download that. Did you download this big file? Because that will take more time.
Yes, sir.
The
That's
virtual
right.
image.
Yes, sir.
Yeah, so if you have the virtual image downloaded, VirtualBox should be very quick. I think if you have Debian machine, sudo apt-get VirtualBox should work.
Yes, sir.
So once you install that, then you should be able to open the file. But again, I mean, it depends completely on you. So you can take your time. We will share the recording as well in case you want to follow it later.
Yes, sir.
Thanks. So I've seen a chat. Manish, have you been able to get the Ubuntu file? Okay, okay. You are on the campus? Oh, you're on IITK. Okay. I don't know what speeds will be there, but let me share the link with you. It was actually there in my email yesterday. I'll have to open the presentation. So I've shared the link here in chat. You should be able to open the virtual machine file now. It's around 20. It's 24.1 gigabytes as I see it. Cool. Thanks. Right. So let's start. So let's understand this example. So this is a two-dimensional case. That's good for us because things will run quickly. Otherwise, we have to wait for the results to appear. It's a multi-material flow. So what multi-material means is there's a sharp interface between the two phases. And when we say multi-phase, like we discussed yesterday, where we have bubbles interpenetrating the liquid or the continuous phase. So both are multi-phase, but we just use this terminology called multi-material versus multi-phase. Multi-material is where you have two phases separated by a sharp boundary. So if you have, let's say, evaporation happening on a surface of a liquid, then you'll have a gas phase on the top and liquid phase below. So that becomes a multi-material situation. Or if you are in fact modeling using the volume of fluid method, if anybody is using that, so that becomes a multi-material for this terminology. So in volume of fluid, what you do is you resolve the complete gas phase versus the liquid phase. You require the surface tension force as well there. So that becomes a multi-material. Okay, so that is what multi-material is. So I'll tell you what the problem is in detail, but it's incompressible. Okay. There is no change in density. It is inviscid, so we are assuming that the viscosity is 0. It is using mesh adaptivity, so we'll see that it becomes very efficient if you're using mesh adaptivity, and it has some detectors to be able to understand what is happening at a given point in space to compare it with experiments. The detector is like you place, if an experiment was happening and you want to measure the pressure at a given point in space, so you put a sensor there. So for numerical terminology, that's a detector. So there's some detail of the problem specification. Let's see if we have some figures. Yes. So this is how the problem looks. So you have a rectangular domain, which is 3.22 meters in width and 2 meters in height. It's a 2D system. You have an initial column of water. So you could assume that there's a wall here that is holding the water in place. Of course, gravity is acting in the negative x2 direction. So that's downwards. So when you remove this wall, this 0.6 meter of wall, then the water will have a tendency to collapse. Because there's nothing supporting it now. So that shear stress will result in the water to collapse, and then you'll get some sort of sloshing. Let's see if we have some results here. Yeah. So you will see something like this. So the water, as time proceeds, will slosh. Then as time proceeds further, it will hit the right wall. It will rise up. Then it will fall back again. And after some time, it should stop. But it's an inviscid case. There's no viscosity here. So there's nothing dissipating the energy. So if you have a completely non-viscous fluid, then it should keep doing this movement. Or if there is some numerical, sometimes you have numerical dissipation happening. So that will result in, after some time, you will have a situation, if viscosity was there, then after some time, you should have a situation where everything becomes stationary. So we will play around with this example. Initially, we'll have a non-viscous or inviscid case. We'll see a sloshing, and then we'll put in some viscosity and then see whether it stops or not. Okay, so let's run this. So let's go back to our terminal. So do a Control C and close the manual. Go back to the main folder, Fluidity. And if I do an ls here, I should see a folder which says examples. So let's open this folder. So cd examples. Do an ls here. So I should see many folders, and we're looking for column collapse. It says water collapse. So let's do a cd water collapse. And now you can see that we have many files here. And that is because I already ran it while I was creating a virtual machine. So let me clean it so that we can start from scratch. So let's do make clean. Okay, so makefile is used for automating multiple commands here. So make clean, basically what it does is it runs these commands that you see on the screen. So it removes many files and so on. So now if I do an ls, I will see only a few files which are required to start with. So if you are installing Fluidity by yourself, you will see only these files, not the ones you were seeing earlier, because they are generated as the code runs further. So we see there are many files. There is a geometry file which has an extension .geo. We have an FLML file, which is what contains all the fluidity settings. So these are the two main files required. So let's open this 2D tank.geometry. Let's look at the geometry. So for opening geometry, we need the Gmesh software. So you can write MSH. That will run the Gmesh software. And then I enter the geometry file name, that is 2D tag and dot geometry. Let's open it. So what that does is that opens the having some problems with maximizing. So this is how the geometry looks. We don't need to worry about it too much right now. What we need to see is that there's a geometry like this. Okay, so rather than writing commands to run it, we'll be using makefile. So if you see, you also have a file called makefile with a capital M. Let's open it. So we need a text editor. Let me see what text editor we have here. So we have a text editor called Featherpad. So if I write Featherpad, that is like a notepad for Ubuntu, and then I write makefile. So that opens whatever is there in the makefile. So what you see is this makefile is automating multiple commands. So we have different makefile options. So one is called pre-process. Okay. And then we have run. Then we have post-process. Then we have input and clean. So clean we already ran. So clean was used to clean the extra files so that we can start from scratch again. Now what we'll do is we'll run pre-process. So pre-process, what it does is it creates a mesh from a geometry. Because for using FEM, we need to create those meshes having elements. Those triangles here for 2D. In 1D, we have simply line elements. Because remember, we have to define those shape functions over these meshes. So rather than writing this complete command, we'll simply run pre-process with make to do something interesting. I'll open a separate screen here. So with this separate tab, let me go back to Fluidity again. So I do a make followed by pre-process. In fact, I don't even need to write complete pre-process. If I write pre and press a tab, it automatically completes the command for me because there's only one command pre-process which starts with the initials pre. Let's press enter. So what happens is, let's look at what we got on the screen. So it ran this command gmesh -2 2dtank.go. So this basically -2 stands for a 2D mesh. So what we are saying is create a two-dimensional mesh on this geometry, and that's what it did. And when it ran that command, gmesh tells us it's running this command. It started on this time and so on. It's meshing in 1D first, then it meshes in 2D. So basically the way meshing works is it meshes the boundaries and then it interpolates or spreads that mesh inside the whole area. Okay, so then it does it, and then it finally tells us it has 19,000 nodes and it has around 38,000 elements. That's the summary of this mesh. And if I do an ls now, I should be able to see there's a new file called 2dtank.msh. It was not there earlier. I only had geometry file. Now we have msh file. So I can open gmesh, gmsh, and then write 2dtank.msh. That should show the mesh now. It's a very fine mesh. If we zoom in, you can see these triangular elements. You can see these right angle triangles that are used for creating the mesh. We can have different kinds of meshes. So right now it created this kind of a mesh. Right? So I will walk around here and make sure people are able to do it. For those online, can ask a question if you have one. Maybe answer already is there. Because it is used for the mistake. Maybe it's already there. Right. So let's proceed from here. So the mesh is working for us. Let's close this and then go back to our make file. So pre-processing is done. The next is to run it. So we can do make run. So when we do make run, what it does is this echo is simply printing something on the screen. It's not a command. The command is this. So it runs Fluidity software with some verbosity. So it V2 says that it will print out some details. V3 is further more verbose. So it will tell me everything. It is entering this loop, leaving this loop, and so on. So that if something goes wrong, you can do some error handling and figure out what happened. So verbosity is a log. It will create a log file so that later, if you want to know the details of how long the code ran, what were the details, you can do it. So minus V0, minus V1, minus V2, and minus V3. So V2 is detailed enough. So and minus L is creating a log file out of it. Otherwise, it prints everything on the screen. So that after some time, it's all lost. So minus L will create a log file. All this information that is printed on the screen while it's running will also go into a log file. And then this water column collapse, water collapse.flml, FLML file is what contains the settings of Fluidity. So we'll look at the settings later. Let's run it first and get some feel of it. So we go back to our command prompt and then we write make run. And now it starts running the code. So I can open a separate tab or go to my previous tab and do an ls now. And when I do an ls, I see that these files with an extension .vtu are getting created. So these were not there because we had cleaned everything. It's also created files which are called fluidity.err that will contain all the errors if there are any. And it has a fluidity.log which has all that details in the log file. You can also do an ls minus L with an H. So that tells me how big the files are. So this is also a new file. You can see it's created right now at 10:46. It's called column-collapse.stat. So it has got many statistics that we'll explore a bit further, a bit later. And then it has all these VTO files. Each VTO file is around 100 kilobytes. And then it has this log file, which has become quite huge. It's become 8 megabytes only in a small. It has lots of information. So my code is still running, but while it is running, I can still start plotting things because you can see that these VTU files already are there. So we let it run for some time. Let's complete and then see. So depending on how fast your machine is, it will take that amount of time. If I go to my virtual machine and see settings, it should tell me, so I'm using 4 processors on this machine that we are using in the lab here. We have a total of 12 cores and we are using 4 of these. So we could have increased that and we could have got better run times. And then we have a memory of, we are using a memory of around 10 gigabytes, which is good enough. Out of 16 gigs, we are using 10 gigs. It run pretty fast. So you can keep doing ls and see that it's generated lots of video files. So let it run. Let's try to visualize. Let's use this time. So for visualization, we have a software called ParaView. So if you write ParaView and press enter, it should open the visualization software. And in this, you go to open, file, open, and then it should give you these video files collectively as a group. Just click it and say OK. So it will take some time to load these video files. Oh no, it's just simply showing memory usage. Okay. So now there's an apply button that is highlighted with green. Press it. So we should see the domain now. And here on the top, there's a drop down. It tells you the different variables that you can plot. So I would want to plot the material volume fraction because that will tell me where is water, where is air. So if I click material volume fraction for water, then it shows me red color and there's a legend here as well. So it tells me red is equal to 1. So red means for water it is 1. So that's volume fraction equal to 1. So there is water in the red region and blue is 0. So that means there is 0 water. That means there is air. These are volume fractions. Okay, remember yesterday we talked about alpha, the volume fraction. So alpha liquid, alpha water plus alpha air has to be equal to 1. So this is the initial configuration, initial settings that we had. And then there's a play button here. If we press that play button, it should play, it should basically run the different, for different times, it will show us the volume fraction. So you can go back all the way and then go step by step. So there is a run play button with, which says next frame. So you click it, it goes 1 frame at a time. So now we can see some sloshing happening and then water sloshes back and merges with the initial interface that we had. So you can actually see this here. You can see an air bubble will get trapped in this region. And it only ran for some time because it is, the software, the code is still running. It is creating more VTU files. So if you want to do some intermediate post-processing, you can do that. Get a feel of what's happening. Now, it has a total of 30 frames. So if I go back to this and I see that it has 28 here. So let's do an ls again. It is still running. So now I can see it has run till 34 frames. So we can reload these files. So I think if I right click water column, water collapse here, it should have an option called reload files. Simply click that and we say find new files. Okay, so now it says max 34. So we have 4 more frames available, and if I click next frame, I can see now that the air bubble has been trapped. That so very interesting dynamics is being shown. All right. Now, in the beginning, what we talked about mesh adaptivity. So if you go to this surface and it says surface with edges, you can see the mesh as well. You can see what sort of elements are being used. I mean, what sort of you're creating elements on these meshes. Those hat functions in 1D. In 2D, it's called a tent function. It looks like a tent, which is peaking at a given node. So these element or basis functions are created on these triangles. So you can see that the triangles are very huge near the top and they're very fine near the interface. That makes sense because the interface is moving. So we want to resolve the interface. So automatically what it does is it resolves the interface by tracking it. And if I go back all the way, in the beginning, the mesh was adapted in such a way so that the interface was, the mesh was very fine near the interface and very coarse away from the interface in the water as well as the air region. And you can also see the anisotropy here. The mesh elements are not equilateral triangles. They are elongated. They are elongated in such a way so that the length is very short in the direction where the change is happening. And the length is long in the direction where the change is not happening. So we are using anisotropic meshes here. So we are adapting anisotropic meshes, which is giving Fluidity an extra edge over the other software. Okay. So these are completely unstructured. They are anisotropic and they are non-homogeneous, of course. I mean, they are fine at some region and coarse in the other region. So let's see if it has completed running. Well, it's still running. No issues. So let's explore there's one more thing that we need to see. That is the stat file. So in these all files, there's something called a stat file. So let's open that. So there's a Python script called stat plot. So we can use that script, stat plot, and then followed by water collapse.stat. There's some problem with this software. So it's just not opening. I don't know if, can you open it? Or does it show a blank for you as well? Showing a blank? So there is some problem with the installation of the software. We'll have to figure it out later. But that doesn't mean the stat file does not have information. So what it does is it has information in an average sense. So let's open and see what it can give us. So it has, on the x-axis, it will have time. On the y-axis, you can have different things. So for example, I want to see the water velocity, the integral of that in the x direction. So 1 is x. So if I do that, then it will plot the x direction velocity on an average, which has no meaning here, but it will plot that. I could also plot, for example, the number of elements. As the mesh is adapting, the number of mesh elements is changing. So I can plot that as well. I'll have information about, let's say, the maximum pressure. I want to see as time proceeds what's the maximum pressure in my domain. So I can plot that as well. So it will plot all these things here. Information is here. It's just a Python script to plot it on the screen. For some reason this Cairo is not installed properly, so that may have a problem. So this is actually a script. So if I go back, so there's a folder called tools. So you can see that there's a Python script called statplot.py. So I'm trying to use an alternative way to see if that works. No, it has the same problem. It's not showing us anything. So that's okay. We will. Let's go back to the folder. So let's go back to the make file. So it's running now. So let's assume it would have a run. And then we have post process. So what post process does is it will run this Python file called plot_data.py. So let's try to run it. Let's see if it runs. So we do make and then post process. So it says the error was it was not able to find the file called watercollapse.detectors. Okay, so that's because it is still running. So maybe this file is not completely created. So we'll have to wait for this code to complete running. Only then we can run this plot_data.py. So this is simply a Python script. You can have a look at it. So this is the script that we run. So what it's doing is it's opening all those VTU files. So each VTU file is basically containing information about all the flow fields for a given time. Okay, so different VTU files are snapshots of flow fields for different times. So it's simply looping through these VTU files and then plotting something on the screen. It is also using this. Let's see if it uses a stat file. No, it's not using the stat file. So we will have to wait for this to run to be able to use this plot file. Let's look at the settings. So this FLML file that contains all the settings that are there for the code, because till now I've shown you a mesh and I'm showing you a post-processing result. But where is that file that contains all the settings? How many dimensions, what discretizations to use, and so on. So for that, we have an FLML file. So if I do an ls star.flml, that should give me this water_collapse.flml. So let's open it. So we can open it in text prompt. It is a markup file. So if I open it in text, what I see is it looks like an HTML code. HTML is also a markup language, and this is also a markup language. So you can see it looks like this. So basically, all the settings are included in the form of a markup language file that the Fluidity code can read. But this is not very user readable. So what we can do is we have a software called Diamond already installed here. So it is for reading this markup language file. So if I write diamond followed by Fluidity water collapse.flml, that opens this diamond file, which has all the details here now for the code. So now I'll want you to follow this and look at this code. Look at the options available here. So this will basically have all the options. So the first one we have is simulation name. So here the data portion is where you can enter information. So the name is water collapse. Everything that gets created will have water collapse followed by something. The problem is multi-material. I told you it's a multi-material type. It's using volume of fluid method. So there are different ways, different types of problems. So what it does is if you click one of these, it will set some options beforehand. So it's only to help you with setting some initial options. So we stay with multi-material, and then the option is for geometry. So geometry, you'll have to set number of dimensions. So you can do it only once. So in the beginning of the new file, you can either set it equal to 2 or 3 or 1. Then you have coordinate mesh. So the mesh it takes from this G mesh that we had created, and that's called 2D tank. Okay, that was the name of the G mesh we had in the beginning. Next, we have some options here. We'll ignore it. Then we'll forget about this velocity mesh and quadrature as well. Quadrature is used for integration. So if you have higher quadrature, you will have a better approximation for the integrals. Then you have input-output I/O. It creates output files with the format of VTK format. So these VTU files are VTK format files. It creates output dumps at a constant interval of 0.05 seconds. So if I decrease this, then I will have more finer resolution when I play the movie. It has a coordinate, well, this we can forget. It has checkpointing. So for example, if I want to run the simulation again, sometimes what happens is the code crashes. The power is gone. Something happens. You don't want to run it again from scratch. It already has run till some time. So we can initialize for that from that later time and then start the simulation again. So this is called checkpointing. It is always recommended in transient simulations or any simulation which is iterative methods, so that you don't have to initialize from scratch and waste your computational time. If you're running problems which take 10 days, 15 days, 20 days, you don't want to depend on the storage, or you don't want to depend on that system running continuously. If you run things on the HPC cluster, it's always recommended to checkpoints, and even you copy those checkpoints regularly to your local machine. So that is, if HPC crashes for some reason, if that information is available, you can start it again from the final dump. So it creates after every 50 seconds, or after every 50 seconds, it creates these output dumps. And then it checkpoints in the end. When the simulation is completed, it will create one checkpoint file as well, so that you can run it further if you want. So these are detectors. These detectors are used to get some information on what's happening at a given point. So we have 3 detectors here. Detector number P2 is at a location x comma y. Okay, so it will measure details of different fields at a given point in space. Because what's happening is your mesh is evolving. And information is stored only on the mesh nodes. We know that. So if you want information on a particular point in space, which may or may not coincide with the mesh. So if you want to do it post-processing wise, you will have to interpolate. And that becomes a very tedious task. So you can put some monitors or you can put some detectors. Some software, ANSYS calls it monitors. We call it detectors. So it's like putting a probe at a given location in space, and it will have information of all the fields at that location in space. You can access that information in a detector file. I'll show you once the simulation has completed. Still running. Okay. Then we have time stepping. So it starts with t equal to 0. It has a time step of 2 into 10 to the minus 4 seconds. It's a very small time step. And it finishes at 2.5 seconds. So that's giving it how long it runs in terms of time, simulation time. This we can ignore for now. This is having settings for adaptive time step. So if you want to have a fixed time step, that is fine. But if you want to adapt your time step based on the CFL number, the Courant number, so you can do that. So we say that we want the Courant number to be less than 2.5. The maximum Courant number in the whole domain should be less than 2.5. So then it sets, it tweaks the time step so that if the Courant number is very small, it will increase the time step. Courant number is getting larger and larger, then it will reduce the time step so that this condition is met. Okay, so let's. So these were all settings related to input and output and time stepping. So we have physical parameters now. The only physical parameter we have is gravity with a magnitude 9.8 and in a direction 0, -1. So that's minus y direction. Then we go to, we have a multi-material. So we have two phases, air and water. So air has a density of 1 kg per meter cube here. Let's forget about this for now. Now the fields we have, so for example, material volume fraction, they are of different types. So they can either be diagnostic, they can either be prognostic, they can be prescribed or aliased. So prognostic means you are solving some equation for that field. And diagnostic means you are calculating that using some other field or many combination of fields. So what's happening here is, you remember that volume fraction of water and volume fraction of air, they add to 1, right? So we don't need to solve for both. We can solve for one and the other is calculated as 1 minus the other one. So what we're doing is, we're actually calculating the volume fraction of water using an equation, using the advection equation. And the air volume fraction gets calculated as 1 minus that. So let's look at the water volume fraction first. So it is using advection diffusion equation, okay, the one I showed you yesterday. It uses spatial discretization. It is using a CV, a control volume scheme. So we discussed yesterday that fluidity allows finite element as well as control volume schemes. Control volume schemes are conservative. The idea is coming from finite volumes. So they're conservative in nature. So since we want the volume fraction to be conserved, we don't want the volume to be lost because of numerical issues. The volume is conserved quantity. So we use a control volume discretization here. This is some sort of scheme that you are using. Let's not go there in detail. And this is conservative advection is used because we are using adaptive meshes. So when we adapt and we create a new mesh, we have to find the solution from the old mesh to the new mesh. We have to interpolate. So it uses some method because earlier the mesh node was somewhere else. Now the mesh node is somewhere else. So how do you find the information at new mesh node given old mesh nodes? You have to interpolate between triangles. It uses some method for that. So temporal, so remember the equations have a partial by partial t term, a transient term, del by del t. So you need a temporal discretization. So we use a theta scheme with theta equal to 0. So theta equal to 0 means it is completely explicit. Theta equal to 1 means it's implicit, and theta equal to half means it's canonical. You can have any theta. It's a theta scheme in time. Okay, so let's ignore that. Then we have initial condition. So initial condition is where you have to specify where is water and where is air in the beginning. So we had specified that in that initial column of 0.6 meter height, you have water, and above, beyond that you have air. So as I said, that fluidity is powerful, that you can have Python scripts into it. So you can have initial condition as you can have a constant value everywhere. You can have a Python script. You can even take information from a file. So here we have Python script. So what it says is, so x is your coordinates, x0 is x coordinate, x1 is y coordinate. So it says if your x coordinate is less than or equal to 1.2, and if your y coordinate is less than or equal to 0.6, in that case, you make the volume fraction of water equal to 1. Else, you make it 0. Okay, so in that small triangle where we had water, if that is satisfied by x between 0 and 1.2 and y between 0 and 0.6. So this is how we specify the initial condition as a Python script. That's it. So that's for volume fraction. And then similarly, we have for now you see velocity here is aliased. So in a volume of fluid method or in multi-material method, whatever you want to call it, we use a single momentum equation. There's only one momentum equation we solve, as opposed to Euler and Eulerian, where we solve two different momentum equations. So here, since we are solving only one momentum equation, so we solve it in the water phase. Doesn't really matter. Here it's prognostic. Then we have some mesh. We'll not worry about that right now. We have a type of equations. You can have linear momentum equation. That's what we want. You can also have shallow water equations, drainage, and so on. So we don't need them right now. Spatial discretization. We are using discontinuous Galerkin, as we discussed yesterday. So then we have mass terms, viscosity scheme, advection scheme. So we can have different schemes from different terms. For example, for advection scheme, we have upwind. Upwinding is used. So we can use different kinds here. If you say none, then basically that disables the advection terms. Then you have viscosity scheme. So we have different schemes here. Then you have which kind of form you want. So yesterday I told you that if you are using a turbulent viscosity, then you want to make sure that the gradient of viscosity is also taken. Because viscosity in turbulent and K epsilon method, the turbulent viscosity is non-homogeneous in nature. It changes with different positions. Okay, so we can use different kinds of forms here depending on what kind of scheme you want to use. So then when you have a linear system, you want to solve it using some iterative scheme. So you can choose that scheme here. You can use this minimal residual method. You can use conjugate gradient method and so on, Richardson method and so on. So there are many options are available for solving linear systems. You can use, we also use preconditioners. So these are, I mean, if you have done a numerical methods course, you'll understand these ideas. But these we don't need to worry too much. I mean, the default settings usually are okay. So we will not worry about that for now. Initial condition. So we say that velocity is equal to 0. It's a vector, so x and y coordinates. So velocity is equal to 0 everywhere. Then we have boundary conditions. So we have boundary condition at the bottom boundary, the left side boundary, the right side boundary. So the bottom boundary we have a Dirichlet boundary condition where the x component is 0 and y component is 0. So that's a no slip condition. And the left boundary, we again have Dirichlet with x component 0 and y component 0. So that's again a no slip boundary. So we have a no slip boundary on the bottom left and right boundary. On the top, we have not used any boundary, so that uses the Neumann boundary. We allow the because of sloshing, some air will want to move out sometimes. We allow that. We will allow. So top is Neumann boundary. So that is partial by partial x and partial by partial y of velocity is 0 there. Not velocity is equal to 0, but partial by partial x and y are 0. So gradient of velocity is equal to 0. I mean, in the direction, normal direction. So this is pretty much it. And then we have pressure. So pressure is also a problem. We have to solve for pressure as well. Then density is diagnostic. We don't solve for pressure, but density diagnostic term is used. So here we are using an internal algorithm. So basically what happens is it's a multi-material case. So density is for a given point in space is simply a weighted sum of the densities of the two phases. Okay, so if you have at the interface, your density will simply be the density of water times the volume fraction of water plus density of air times the volume fraction of air. And this here we have settings for adaptivity of the mesh. We'll not worry about it right now. So this is CFL number. It's a diagnostic field. We calculated using other fields. This is calculating divergence. This is basically used to make sure that the overall continuity is satisfied. So we calculate that and check for the summation of the divergence of the velocities of the different fields weighted by the volume fraction is 0. Let's see if it has now completed running. Good. So we can see that the simulation has completed. And detector file still is. Let's run the post process and see if it does something. It has some problem with detector file. So what I will do is, I'm not sure what's the problem. I will simply rename it. So I've copied it into a new file, and now I will run post process and hope it is able to open it. So it has some issues with the detector file. So we will not ignore it further, but it's creating some PDF files. So it seems that our post processing has created some PDF files. So let's look at PDF files here. So let's try to open it. Right. So we can see that this Python script for post processing is actually working. It works on different in steps. So it was able to work in the first two steps, and then it had some problem. So this is generated. I mean, let's see when it was generated. So this was generated at 11:21. So that is, I think, just 1 minute ago. So this is generated using the script, and what it is telling me is, as a function of time, at a given point in space, what is the water depth? So that means it's not a point in space; it's basically a section. So it's telling me at a given section what the water depth is, and that is at x equal to 2.725. So that was in the whole domain. If you look at it, it was somewhere in the middle or towards the later side. So initially, the collapse happened. It was flowing from left to right, and as soon as it reaches that x coordinate, the water starts to rise there. We see that this is the dashed line is what fluidity gave us, and the circles are what we have from experiments. That's already available in the folder, and we are getting a decent match at that position H1. So let's look at H2. So this is for H2. Again, a decent match. So you can see that you can automate this whole process through a Python script. Now, if you want to understand how this Python script works, you can go to the Python script and look at it. And later, when you create your own simulations, you can, rather than plotting it every time separately in a different software, you can write these scripts, and then you can change the code, and you can have this make file kind of a system where it automates the whole process. So this pre-process, run, and post-process, they can all be combined into one step. So basically, if you want to test, for example, different discretizations, and you want to see which one will give you a better result, so you create different folders. Each one has a different discretization in the FLML file, and then you do a make complete run in the first, second, and third. And then what will happen is after you give the command and you come back after a few hours, you will have 3 PDFs ready. You can simply open them and compare. So that's the level of automation that we have. So that's recommended as opposed to running it many times and then plotting it again, wasting time in that. So you would rather spend time in thinking what's happening with the method rather than every time manually doing things. Because if you try to plot it every time, then you get tired mentally doing that, and you cannot think of the actual work that you want to spend the time on. That is, which discretization is the best one. So spending that time in automation is always useful if you want to um, save time later. And again, these are all Linux commands, so you can actually have a bash script which runs, creates different folders with settings, and then it will run all of them at the same time. That's another level of automation. So depending on your understanding of Linux systems. Good. So I think I have discussed. So we've discussed the problem. We have talked about a diamond, which is used for setting the FLML options. We've talked about geometry and meshing to some extent, and we have talked about post-processing as well. So now what we'll do is we will modify this problem. Yeah. So let's modify this problem slightly and then run it for some time. So let's so I don't want to change the settings, so I'll copy the FLML file. So I'll call it water collapse 2.flml, and now we'll make changes into it. So this time what we'll do is, firstly we will, so it was running from 0 to 2.5. So I'll reduce it. I'll reduce it to 0.5 seconds only. And save it. The other thing I want to do is I want to set some viscosity of water. Okay, so right now the viscosity term is disabled. It's gray. So let's enable it. And then we are prescribing the viscosity value. So I prescribe the value as an isotropic. So it's simply a constant. Let's call it, let's make it high viscosity of 1 Pascal second. So water has a viscosity now. Air still has viscosity. Sorry, there's only one field here. So we both the fields, air and water, have a viscosity of 1 because we are solving for only one momentum equation. So we have set the viscosity as 1. So we are making two changes here, reducing the total time so it runs quickly, and we are setting the viscosity as equal to 1 for in the water phase. Let's save it. Now the thing is, I do not want to get rid of these video files because I'll want to compare the results. So I'll go back a folder and then I'll copy the whole folder water collapse. For this, I'll have to use a -R recursively, and then I'll put it into water collapse 2. So that simply copies everything into water collapse 2. So now if I do a make clean, it will remove all the VTU files, but I will still have the VTU files in the water collapse 1 folder. So I will show you how we can compare the two when the simulation is completed. So now since we have renamed the water collapse file, so make will only work for the, so let's modify the make file and do it in leaf pad or feather pad. So in this case, the mesh is still the same. We're not touching the mesh. What's happened is the name of the FLML file has changed from water collapse to water collapse 2. So I've simply changed that here, and it seems everything else remains the same. So let's save it. Close it and do a make. So what I'll do is I'll add something called complete. So now that complete will run pre-process, it will run, and it will run post-process. As I said that we can now automate the complete process. So we have modified the make file now. And now I will type make complete. So it ran the pre-process first, and now it is running the run. So it is actually running the command, and once it completes, it will run the post-process also. So this is automating all the 3 steps into just one command. So I did not open the software, I did not open Diamond, I did not open Gmesh. I simply ran one command, and it will run the whole framework, the complete process now. So I can see that it's completed some part of it. You can see that these checkpoint files are also getting created. So these checkpoint files are the ones with the information about if you want to run it again. From this, you can initialize the whole thing from a checkpoint. So this checkpoint, you can see this new FLML is created. FLML is the one that we used to initialize. So rather than running the initial FLML, which initialized everything from 0, you can run this FLML, automatically it starts from that point. There's nothing that you need, everything is set there. You simply need to write fluidity followed by this checkpoint file.flml, it will run. That's the good thing about creating checkpoints. Is it completed? Yeah, so it completed. So I can see these PDF files that are created. So these are created 2 minutes ago. I guess these are latest ones. So well, we ran it for only 0.5 of a second, right? That was this time. So this is not showing much here because it's a flat line here. Had I run it for a longer time, it would have shown. So you can see that it's different from what we had earlier. The best thing is to look at the animation part. So that's what happens. If we had run for a longer time, we would have seen more interesting dynamics. And now I would want to compare it with the previous case. So I can open the water collapse, the earlier one, not the number 2, and then open the VTU files here. Apply. So they open on the right side. And then I can open material volume fraction. So if I go back, they are now synchronized. Well, this one has till 50 and this one only has for a shorter time, but that's okay. So let's so you can see there's a difference now. You can see that this starts to rise. It's like a very viscous fluid showing different dynamics. Air is already getting trapped here. It's a highly viscous fluid that's flowing, whereas this one is completely non-viscous. So the dynamics are slightly different. Had I run it for a longer time, we would have seen more interesting dynamics happening here. But you can see that they are differing in the physics. It only ran till this time. So this is the time it ran till, and they are definitely showing some difference. Okay. If you want to run it further, you don't need to run it again from 0. You can look at the final checkpoint. So it has a checkpoint. Let's look at the FLML files. This one is a checkpoint we have. So let's look at this checkpoint. So time stepping, current time is 0.5 second because it's already run till 0.5 second, and then finish time is also 0.5. So I can change it now to 1 and save it. And now I can run. Well, so now we only need to run this part, but the file name has changed. So rather than doing this, I will run fluidity directly. So fluidity is installed in bin file -v2 -l for log file, and then water collapse. What was the name? Water collapse, water checkpoint. Water collapse. 10. That's it. I can put an ampersand, it runs in the background. Now I can see to top that it's running, it's taking 100% CPU, it's running Fluidity. So now we can see that it has VTU files which have checkpoint underscore 0, checkpoint underscore 1 and so on. Okay. These are new VTU files that are getting created. You can open ParaView. Then let's open the, not this one, this is the old one. New VTUs are these ones. Well, these ones, sorry, as a group. So this is where it started with, and now it's going further. Okay. Any questions till now? Yeah. Say it again. Ah. So you're saying that how do we identify the interface? I don't know, so we can check. So let's see. Usually, you are right. For calculating the interface, we take alpha equal to 5. That's typically what it does, what we do. But we can check the Python script. What are whoever created this. This is a function that is being used. So this get water depth. This is, I think this is what calculates the. It doesn't seem that they're calculating the water depth here, although they're getting it from somewhere. Hmm? This is the function, but this is numpy.a range delta by 2 comma 2 plus delta by 2. Not sure what it is doing here. We'll have to understand it later. But typically, what we do is we find wherever the volume fraction is becoming equal to half, and then we use that. Okay. Maybe it's already. It is calculating here. I can see that. It's doing something to the volume fraction and multiplying it by delta. So doing something. We'll have to understand a bit further. Maybe it's using a different method of doing it. So either you can find it wherever the volume fraction is half, or you can find it through change. So wherever there's an interface, there's a strong change in alpha. So rather than looking at the value of alpha, you look at the gradient, the change in alpha. That could also have been used. I will look at it later, but right now I want to be recording this webinar. So there is this is definitely this is calculating the. What was the other question? You had two questions.
Calculating transient is like essentially like take from BTK file data.
Yes, for every time step. Every time step information is there in the VTK file. So it is opening those VTK files. There's a loop there. It loops through all the VTK files. A simple loop. Good. So we have spent a lot of time understanding the framework, but now that we understand it, we will go to our population balance problem because that was the main aim here. So let's go back, and right now we'll come out of the examples folder. We'll go to the tests folder, and test folder will have lots and lots of files, but we are looking for something that starts with popbal. So we have a couple of folders. So it says popbal homogeneous, popbal non-homogeneous, popbal non-homogeneous with different schemes. So let's go to popbal homogeneous, which has breakage and aggregation in it. So now what we see is it has an FLML file, and since it is homogeneous, then the mesh really is not important, but the SRC file, source files, will have a geometry in it. So I can open the geometry. It says minimal.geometry. It is simply a triangle. Okay, because it's homogeneous, the spatial effects are not relevant here. It is simply solving for breakage and aggregation processes, not how they are varying in space and time. How they are varying in space. Time, yes, not in space. So we have some geometry, but on every node of the geometry, we have the same thing calculated. We don't have to worry about this right now. So we have a make file here as well. Rather than writing the commands ourselves, let's see. So what it does is it make input will run a command where it generates a mesh in an optimized binary sense. So we'll simply write make input. It's run, it's created a mesh. And now what I do is I run the FLML file. Let's cancel it and run it in the background with an ampersand sign. So now it's running in the background. I can see with the top command, it's running fluidity. And with an ls, I can see that VTU files are now getting generated. So now we can see that we have lots of fields available here. We have the weights, two abscissas, 4 moments, and some, since we are comparing with analytical results, so we have some difference as well with analytical result. So here it's all homogeneous. So let's look at moment 1. So since it's homogeneous, the solution is the same everywhere. It will make more sense if I look at it in stat plot, because then it will plot things with time. But stat plot, for some reason, it's not working for us. So we can look at it here. So what we see is that now the value of the moment is increasing. So moment 2, for example, is constant. Actually, moment 3 should be constant. That's the volume. Because if you break particles and aggregate particles, their total volume will not change. Their area will change. Their number will change. So number is m0. So that m0 we see it's changing. M1 will change. M2 will change. In fact, M2 should also change. If I go further, I think it's too short a time. We'll have to reload it. So this one takes longer time because now you see that you are solving many equations. You're solving equations for two weights and two abscissas as well, in addition to other equations. So this is taking time. Let's look at the FLML file. So here we have the material phase, which is fluid. Now the velocity is prescribed. We are not solving for Navier-Stokes equation here. We are prescribing the velocity, and that velocity is prescribed to be 0. So there is no flow happening here. It's only you can think of the problem as some sort of a well mixed system where there is no flow happening and no net flow happening, where the particles are simply, some crystallization is happening. Particles are growing, as well as because of some reason the particles are breaking down as well. It's happening together. Okay. So we have analytical result for this particular problem that we have. Analytical results are available. So we prescribe the value as a Python script. So this is the expression for the analytical result, which uses some tan hyperbolic and so on. So we can specify the analytical results here. So we have M0, M1, M2, and M3. Then what we do is we create a diagnostic that is simply a difference of the analytical result and the one that we are calculating. So we are setting it as it's called scalar difference, and that difference is a difference of the analytical and what we are calculating. And we do it for the complete set of nodes that you don't need to worry about. Now let's look at the actual population balance options, because that we haven't looked at yet. So here we have abscissas, we have two weights. So in this case, the number of DQMM nodes is 2. So we need two weights and two abscissas. Now how do we initialize the problem? We need to tell in the beginning how many particles do we have. What are the 4 different moments, or what are the 2 weights and 2 abscissas. So you can initialize the problem using either moments, or you can use the weights and abscissas. It's up to you. If you use moments, it will use a product difference algorithm that goes from moments to weights and abscissas. If you use weights and abscissas, that is what it needs. So we are saying that we'll initialize the initial conditions from moments. So we have the moments here. So moment 0. So we have to specify initial condition here. So we have a constant value for moment 0. For moment 1, we have an initial condition where the value is, now it is using a Python script. So it's calculating as 6 by pi times to the power 1 by 3 times some constant. So you can see that you can calculate this, rather than calculating outside and feeding it here, you can specify it as a script here. So moment 2, again specified here, and moment 3 is 6 by pi. So we specify the initial conditions. Now the weights and abscissa, the 2 weights are prognostic, because we are solving for the weights in population balance equation, and we are also solving for weighted abscissas. Abscissas are not being solved. We have a diagnostic value here, so that is getting calculated. So we solve for weights and weighted abscissas and calculate abscissa as the ratio of the weighted abscissa and weight. Okay. So these are prognostic fields. So we have we are specifying initial condition, but we don't use it because we are using initial condition from moments. It has temporal discretization. The theta is using a Crank-Nicholson scheme here. Spatial discretization. It uses a continuous Galerkin method. So you can see that we are excluding advection term because velocity is not there now. There's no point wasting computational resources on advection terms. So we ignore that. Now the question is, we need physical closures for breakage and aggregation. So where do we specify those closures? So those closures are specified here in population balance source terms. So we have aggregation. We specify aggregation frequency, which is a constant aggregation frequency of 1. It's a very simple system for testing. And then we have breakage, where we need the breakage frequency, which in this case is a power law breakage. So the breakage is of the form of some p to the power of p times of constant p times the abscissa times to the power of r. So the coefficient p is equal to this, and the power is 3. Okay, so this is the kind of breakage we are using. Again, this is very theoretical because we want some analytical solution out of it. And we also talked about the daughter distribution function. When a particle breaks, it forms smaller daughter particles. So what is the probability of forming a smaller daughter particle of a given size given a bigger particle breaks? So for that, we are using a function which was specified by McCoy and Madras in their paper in 2003. But we have other options as well. So we have symmetric fragmentation that we can have a particle breaking into 2 equal size particles. We can have the kernels that were specified by Lagonen in 2007. So these are the kernels specified for turbulence. So this uses turbulence dissipation rate as well. But for this problem, we are using McCoy and Madras. For breakage frequency, again, we have other options available. We have constant breakage, we have power law breakage, we have the breakage specified by Lagonen in their paper. Aggregation, again, we have options available for aggregation frequency. So we can have constant aggregation, we can have hydrodynamic aggregation, some aggregation, and we can have the aggregation specified for bubbles in the Lagonen paper. Is that clear? So you can see that all these options are available. You can choose whichever we want. And then for numerical reasons, sometimes we get the A alpha equal to D. The matrix A becomes ill-conditioned. That is, its condition number is such that it becomes extremely sensitive to the conditions. So if you change your D right hand side matrix slightly, your solution changes significantly. Okay. So for that, we have to do something. Otherwise, the solutions can be very non-realistic, non-physical. So we have different ways of handling it. We either set the sources to 0, or we, this is for checking for the ill conditioning. We can also perturbate. So we can slightly, so what happens is, so when 2 different rows become the same, when the condition number becomes, it becomes ill conditioned. So then we can do is, we can slightly perturbate. So see, when you start, your A matrix depends on different abscissa values. Now when you start a system with monodispersed system, all the particles have the same size, which is very realistic. Then what happens is your matrix becomes ill conditioned. So what we do is, we mathematically change the value of one abscissa slightly. So if one is equal to 2.0, the other becomes 2.001. So that perturbation results in getting out of ill conditioning. And then as time proceeds, the distribution will change because of aggregation breakage, then it becomes fine. Okay, so we are perturbating the abscissas just to make sure that that monodisperse initial condition, the initial condition is such that our A matrix is ill conditioned, so we can perturbate it and get out of ill condition. But if your physical solution requires the system to be monodisperse, it's always monodisperse, then there's nothing we can do. It will stay ill conditioned always. Okay. You have an option to set minimum weight. If the weight is smaller than that, because you're dividing weighted abscissa by weight, so that division by a very small number close to 0 can again result in problems. So if the weight value is less than 10 to the minus 10, we make it 10 to the minus 10. That's again to get rid of some numerical issues. There are many other options available. I am not going to discuss all of these, but as I said, that the manual, the PDF manual has details of everything. You can go to that manual and then you can look into it. Okay, so we are getting towards the end of the first session. So I wanted to cover the bubble column problem as well, but did not get time. So what we'll do is in the 1:30 session, I will show you the bubble column file. We will look at the geometry. We will look at how to change the geometry briefly, and we will look at the settings in the FLML file for bubble column, and we will run it. And then, of course, I mean that problem takes half a day to run or maybe 1 day. So we cannot do it right now in the session, but I will show you the settings and then leave it to you to run it yourself. And results we already have seen, so there's nothing to see in the results. But the settings is something we'll show you and we'll give it to you. Okay. And we'll also demonstrate very quickly how to use population balances in ANSYS Fluent. For those who are online, may not have access to Fluent. I'm not sure about it. For those here, we'll try to get you access on the machines. If not, then you can look at it. We'll look at the screen here, and you can follow it up and then try yourself later. ANSYS Fluent has a very good manual for, a PDF manual available on their website for demonstrating how to use population balances. Right. So, do we have any questions? Sorry, say that again.
Screen of the model design.
You mean screen?
Here the only value.
Yes, yes.
So if you want to compare the possible
To physics. Can you give me an example as to what are the physics would you want to include?
laminar flow transfer both.
Yes, yes, yes. You can do that. Yeah. Energy equation you can include. Yeah. No coding is required. No, no. So the question is, if I want to include multiple physics. So right now we showed you population balance, and the velocity is not there, but you want to include, let's say you want to include velocity, which is getting calculated using some for some situation. Okay? So we can do that. So we will show you in the second session with bubble column that we'll be solving for Navier-Stokes as well as we are solving for K epsilon turbulence, and we are solving for population balance. But if you want, you can include heat transfer as well. Okay, so that is allowed. So heat transfer is going to be included as an advection diffusion equation. So we include, let me see if we have it somewhere here. So we'll have to include a scalar field temperature. Heat transfer is basically solving for temperature, right? So you can see that this temperature has been included. So now it's a prognostic, you're solving for it, and then you can have different terms, the conduction term, the convection term. So it's an advection diffusion type, so you can have a heat transfer type. So then it will take care of all the terms. and some coupling because it's an see heat energy equation is again a transport equation. It has a conduction term, right? So which is the diffusive term. It has a convective term, which is the advection term that you have, and then it has a source term, which also we can include here as source terms. I think source terms can also be included. So you can include source term. So if heat is getting generated because of some electrical heating in the system and so on. So all these, in fact, we have examples where heat transfer is also getting solved. So you can look at those examples. But ultimately, it's the Navier-Stokes is slightly complicated because you're solving for velocity and pressure equations coupled to each other. But advection diffusion for temperature is, if it's uncoupled, it's very easy. If it's coupled because of buoyancy, you can include that as well. So buoyancy terms can be included as well. Options are available. So buoyancy is also available here, so you can include. The buoyancy does some coupling between the flow. The question is, can we include global parameters? It is not a program. This is a software that's being enabled for you. So it's a CFD software. For a CFD software, why would you need a global parameter? You have to define density only once. You don't have to define density different for different situations. Yes, yes. Density is for a fluid. So see, what happens is you have different phases here, and each phase has an equation of state. The equation of state will tell you what sort of density you want to use. Okay, so it's incompressible with a certain density. Now, if you want temperature dependency, you can have it here. So now what it does is it calculates temperature in the temperature equation, and it uses that to calculate the density here. But density is a property of the fluid, so it gets calculated only once in the fluid. Okay, and then that fluid has a velocity. The fluid has some population, so it has different moments. It has temperature. It has pressure also. We haven't enabled that. Pressure is also there. So this is, the framework is very intuitive in terms of physics. So it has a fluid, has density, the fluid has different properties. So everything is there. Now that property could be prognostic, you could be solving for the property, or the property could be prescribed, or the property could be calculated from something else. That you have to specify whether the property is prognostic, prescribed, alias, or it could be diagnostic as well. Okay. I hope that answers your question. Any other questions? For those online, is there any question?
For me, I'd have to follow the instructions after installing everything into my Linux.
Sure, sure. You can always, I mean, anybody here can get in touch with me over email.
Yes, sir.
With your questions. Good.
Yes, sir. Thank you, sir.
Right. Thank you very much. So we'll close the session now, and we'll have another session at 1:30. Should we delay it? 1:30 is a bit early. Can we do it at 2 o'clock? So let's meet at 2 o'clock. I hope that works for online as well. Yeah, good. So we'll meet at 2 o'clock now. From 2 to 3, we'll look at further bubble column problem and then look at answers. Thank you.